So moving on, what we did last time, we are going to do uh, kinetics in tangential and normal coordinates. Okay, so the same thing, drawing free body diagrams, equations of motion, and kinematics, but in the tangential and normal coordinates. And really the key is to recognize that tangential and normal coordinates are required in order to write the kinematics. Okay, and so before I start with problems, let me review a few things about normal and tangential coordinates. So normal and tangential coordinates are the coordinates of choice when you can express the position of the particle using something like S, which is the coordinate which describes the path of the particle with time. So if you want to draw a free body diagram for this, it will be, well, there'll be forces in, so this is a free body diagram for that particle. Let me draw the coordinates first. So since this particle is curving, the radius of the center of the curvature of the curve is somewhere on over here. What I need to do is I need to specify un in the direction in which the center would be, and the tangential direction is always in the direction which the particle is going to move to. Okay, so once I specify that, what I do is I write forces in the normal and tangential direction. Okay, so this will be forces which are external to the particle, okay, not internal. And the path, this path is something like this. So then this angle here is theta, and that is essentially, I'll put that in a minute. So that's theta, and I'll write theta in a bit. But write the equations of motion. Okay, I'm going to abbreviate the equations of motion as EOM henceforth. The summation of the forces in the normal direction is mass times the acceleration in the normal direction, and the acceleration in the normal direction is the velocity dot. So it's the rate of change of velocity or acceleration. Similarly, the force in the tangential direction is mass times acceleration in the tangential direction, and the acceleration in the tangential direction is v square divided by rho, the centripetal acceleration. Okay, and a few things to note. Rho is the radius of curvature that can be found out if you know the equation of the path. If you know y equals f of x, then rho is simply 1 plus dy dx square, the whole thing cubed, and then take the square root, so 3 divided by 2, divided by d square y by dx square. So there is the modulus of the absolute value, which means that if d square y dx square comes out to be -3, the mod makes it positive, so that the radius of curvature rho is always positive. It's never negative. And the theta, which I put down over here, is simply tangent inverse of dy by dx. Okay, so again, what you know is that this curve is y equals f of x, and once you know that, you can then find the equations of motion, but you got to find rho and theta. Well, theta would be needed if you want to resolve the forces in the normal and tangential direction. Yeah.
So what is the tangential acceleration equal to v dot, and the normal acceleration equal v squared over rho?
Oh, I think right. My bad. Good catch. The easiest way to do this is wrong. That's the normal, right? Oh, no, that's not right. So the tangential is this. That's right. No, this is right. Yeah, the normal is v square. Yeah, is that clear? It is this what it is. Yeah. Okay, any other question? Okay, so as I said, this is the same recipe we used last time. When you see a problem, first you want to identify if it's a f equals ma problem, and the way to do it is to ask yourself, would you need to find that? Are forces given to you? If forces are given to you, then yeah, you have to use the kinetics formula, f equals ma. So draw the free body diagrams, okay? Recognize that this is going to be normal or tangential components, so there'll be Fn and Ft, so you need to draw a coordinate frame in the normal and tangential direction. After you do that, then you write the equations of motion in the Tn frame, like I've written so, and then if required, then you might have to integrate the equations to get positions and so on, okay? So same recipe as last time, except normal and tangential coordinates. So let's start solving some problems. Okay, so there's a pendulum. Bob B has a mass m and is released from rest when theta equals 0. So it's released in the horizontal position. Determine the tension in the string BC. So you're going to find the tension in the string immediately afterwards, so immediately when it's released, and also at the instant when the bob reaches an arbitrary position theta, where theta is measured with the horizontal. So one thing about the book is that it never really draws gravity, but all the problems in the book are, you could assume that there's gravity pointing downwards. So there is gravity downwards. Okay, if in the exam I don't give you gravity, please ask if there's gravity or no gravity. This thing cannot fall if there's no gravity, so it's really pointless. But I think that the book should put gravity. They just have no gravity in any problem. They don't show gravity. Okay, so first of all, is it a kinetics problem? Yes, it is, because this is acted by a gravitational force. It's going to move due to gravity. So we have to use F equals ma. Now, what is a good way to do this? Rectangular coordinates we learned last time, we can use that. It's perfectly fine, but this is probably simpler to do in tangential and normal coordinates, because there's a path S, which is there's a normal and tangential force on the string, and it's most easiest to resolve it that way, because you can see that the normal component is going to give you the tension in the string. So this is a problem where you do kinetics in the normal and tangential coordinates. So free body diagram. Okay, so there is a ground, there's a string, and there is a bob. So you have to decide what you want to draw a free diagram of. I think the bob would make more sense, because you're given that there's a mass and you want to find the tension. So what I'm going to do is draw the free body diagram when the bob is at a random angle theta. Okay, and then in order to solve for the horizontal position, we can just put theta equals 0. And we can actually solve for theta equals theta and theta equals 0 easily. So I'm going to draw the bob in a random orientation theta. Okay, and what I do is I cut the string. So when I cut the string, there's going to be a tension in that direction. Okay, cannot be the opposite, because the string can only take tensional forces, cannot take compression. There is mass times gravity. Okay, and since we recognize that this is a normal tangential coordinate problem, I have to draw the unit vectors in the normal and tangential direction. So un always points towards the center of the circle, and ut is in the direction in which the bob would move. Okay, so that's about the free body diagram. That's all. So So the equations of motion. Okay, so what am I interested in? Well, I'm interested in finding the tension. That's one of the questions. So let me not write ft because I'm interested in t. So I'll write Fn equals mass time An. Fn is tension, that's in the un direction. What else is the external force? Is there any other external force? Mg sine theta. So let's see how we get mg sine theta. So mg acts vertically downwards, but we need to find the force in the normal direction. So I need to find, well, this is going to be theta, and this is going to be 90 minus theta. So it's going to be mg, the component in the normal direction is mg cosine 90 minus theta, and mg cosine 90 minus theta is mg sine theta. So that's right, mg sine theta. Well, if you want, you can write it as cosine 90 minus theta equals mass times the normal acceleration, which is v square divided by rho. Now it turns out that rho is simply the length of the string, because this is going to move in a circular path. You know the radius, it's the radius of the circle, which is in this case is the length of the string. So that is t minus mg sine theta is mv squared divided by L. Okay, now in order to solve for tension, I need velocity, and I don't know what the velocity is. So how can I find the velocity? Derivative. That is not adding more information. Okay, I just wrote equation in one direction. There's another equation I can write, right? So that is the ft equation, that's mass time acceleration in the tangential direction. Let's see if this equation is able to give me velocity. So what's the net force or the external force in the tangential direction? Does tension act in the tangential direction? No. Mg does act in the tangential. So it's Mg. Again, it's going to be the tangential component. So it's going to be Mg sine 90 minus theta, right? Which is Mg cosine theta. Also, this Mg cosine theta would act in this direction, right? It's going to act in this direction. So it's going to be positive, equals mass times velocity dot. Okay, so that equation is an equation for velocity dot. So perhaps by integrating velocity, I can, velocity dot, I can get the velocity and sub it in the first equation, or this equation 1. So the last step is kinematics. V dot is g cosine theta. Okay. So what I need to do is I need to find velocity. There are a couple of things I can do. I can find velocity as a function of time, in which case I'll write v dot as dv dt. I could also find velocity as a function of theta, or s, or r, whatever you like to say. And that I think is more useful because there's nowhere in the problem am I told about time. So what I'm going to do is I'm going to write one of the formulas which we wrote for velocity, which is dv ds, right, is equal to g cosine theta. So if you remember, v dv is a ds. That's the formula I've written down. Better way to write it would be v dv ds is a. Okay. Now I cannot quite integrate that because I have theta and then there's s. But s and theta are related because s, what's s? S is basically the arc length. It's this. It's the motion of the particle of the bulb. Okay. So can you find a relation in s and theta? So it's radius times, the radius is L, and the angle is theta. So S equals L theta is the relation for arc length as a function of theta. So ds is L d theta, right? So put in 3, we have d b dv equals g L cosine theta d theta. Okay, I have to integrate this from this bob starts with the velocity equal to 0, and then the final velocity is v, which is an unknown. The initial angle is 0 horizontal, and the final angle is theta. So if you do that integration, you get, you should write the answer. It's v square equals 2gl sine theta. Okay, so let's call this 4. So all we have to do now is put 2 in 4 put 4 in 1, this equation, to get t equals so I get t equals 3 mg sine theta. Okay, so that's the tension at when the bob is at an angle theta. When the bob is horizontal, theta is equal to 0, and so the tension is going to be 0. You also asked to find the tension when theta is 0, so t equals 0. Okay, so to summarize, this is first you identify it's a kinetics problem, then you think of what coordinate frame to use. If you think it's normal tangential, then you draw a free body diagram using the normal tangential frame. Then you write the equations of motion in that frame, and then if required, you can do the kinematics. That's optional. Is it clear? Okay, so 0.8 mg car. Okay, 0.8 mg, I just don't understand the notation of the book, but when it says 0.8 mg, that mg means it's 800 times g. So m implies 1000. I don't know from where they got that, but that's what it is. So 800 g car travels over a hill having the shape of a parabola, and this is the equation of the parabola. When the car is at point A, so this point, it is traveling at 9 meters per second. So the velocity is 9 meters per second. Let me write that down. Velocity is 9 meters per second, and increasing its speed at 3 meters per second square. So that means that the acceleration is 3 meters per second square. Okay, find the resultant normal force and the resultant frictional force that all the wheels of the car exert on the road at this instant, and neglect the size of the car. So, well, this is a problem where they've given you a hint. They've already told you it's a normal and tangential coordinates problem by giving you the velocity at velocity dot. Okay. So since you have to find the forces, it's clearly a kinetics problem. So let's get started with the free body diagram. So that's the car as a particle. Again, the book doesn't give you gravity, but there is gravity. So that acts vertically downwards. There is going to be, you're told to find the normal and the frictional force. So clearly there is a normal force. Let's call it Fn. And then there's going to be a frictional force, in which case it's going to be in the tangential direction. So since it's curving towards the top, ut is going to be, well, un is going to be towards the center of the circle, not circle, but the changing center of that particular arc. And the tangential component is going to be in the direction in which the car is moving. So that's right. And let me draw the shape. The shape is, this is the parabola at this instant. And what I'm going to do is, I'm going to write theta because I'll require theta to resolve mg in the x and y direction. So if this is theta, then this also is theta because this angle is 90 degrees. Okay, so we have the free body diagram. Am I missing something? Okay, it looks like it's good. So let's write the equation of motion. Okay, so again there are two equations, one for the normal, one for the tangential direction. So Fn is mass times An. The normal force is Fn acting in the direction opposite to Un. So I'll put that with a negative sign. There is mg, which is acting downwards. I need to resolve it along the normal direction. So that's going to be mg cosine theta. And since the force is going to be, when I resolve this, it's going to be in this direction. This is going to be positive because it's in the positive un direction. Equals mass times the normal component of the acceleration, which is simply v dot. Oh, that's tangential, that's right. V squared divided by rho. Okay, that looks right. Summation Ft is mat. So the tangential force, okay, so I drew the tangential force in this direction because it's a friction force. And how does the friction act? It always retards motion. It always acts in the opposite direction of motion. So the car is going forward in the ut direction, and the friction is opposing it. That's why it's in the negative direction. So minus Ft is the tangential force because it's in the negative ut direction. And then there's mg sine theta. It's this direction. Mg sine theta is in the ut direction, so it's positive. Equals mass times the rate of change of velocity. Okay, so I need to find Fn and Ft. Okay, if I want to find F and Ft, I better know all other things. So I'm given velocity dot, right? I wrote it down right here. I need to find, I'm given the mass. I need to find theta and rho, and then I'm done. So rho is 1 plus dy divided by dx square, the whole thing 3 divided by 2 divided by modulus d square y by dx square, and theta is, as I wrote down earlier, it's simply tan inverse of dy dx. Okay, so this is y. So y is 20 times 1 minus x squared divided by 6,400. So dy dx is 20 times derivative of 1 is 0 minus derivative of x squared is 2x divided by 6,400. And then, so this is 16, I think. So it's minus x divided by 16. or 160? 32? No, there's 2 here and there's 2 there. So it's 4, right? So 160. And then d square y dx square is minus 1 divided by 160. Okay, so theta is tan inverse of dy dx, so that's minus x. I need to find x, so I'm given that x is 80, right? The x coordinate of a is 80. So this is going to be minus 80 divided by 160, so that comes out to be 26.57 degrees. So then you can find sine theta, cos theta, right? So once you know, so you basically can find rho because you know dy dx and d square y dx, and all you got to do is put x equals 80, and then you know theta. So you can find sine theta, cosine theta, and so all is left is find Fn and Ft. Fn comes out to be 6.73 kilonewton, and Ft equals 1.11 kilonewton. Okay, so again, to summarize, recognize it's a kinetics problem, and then you need to use normal tangential coordinates. Once you do that, you use a recipe, free body diagrams, show the forces in the normal tangential direction. First you draw the normal and tangential coordinate direction, then write the equations of motion, and optional, in this case we didn't have to do it, to do the kinematics.